account, and you should as well. Especially when you have an email with BioPharm at the end. It's a very long thing. But no, thanks for Natasha for having me. It's a really honor to come speak to the kids and the students and kids that we're relying on as our business to be employees and be interns and be as well as the future of our company and Dale. So I just want to reach out and hopefully we can form partnerships and relationships. Natasha had on her slide, tell about where you came from, how you got there, your different career paths and all that, and how different things changed, and how your path's not very linear. When you went into a STEM career, I'm a poster child for that. And so I was going to see a couple slides on how I became a director of engineering in bio. I grew up in North Carolina, born in Hickory. So I was down, I was actually a furniture town. But then my dad got a job in banking down in Charlotte. I mean, back in the day, it still was a pretty big hub. I mean, it is the hub for banking. You have Wachovia, First Union, TEP, which is now Nations Bank, which is now, so it's all the big banks were down there as well as all the small banks. And so I grew up, my first career path was, what do you want to be when you grow up? Banker, right? That's what your dad does. You're going to be what your dad. So I was like, okay, that's good. So get through high school. I'm in Mecklenburg County with a nice competition, kind of like, that you're competing for 3 spots in every college, for Mecklenburg County. So my family tradition was, you go to Carolina. You go be a business major in Carolina. My brother was, my dad was, my aunt was, my uncle was, family everywhere, healed everywhere, right? So talking about a career path change, roadblock, didn't get in. So first career path change. So I'm like, oh great, I became the black sheep of the family. You're the first one to go where? To the rival. Right? And so I'm like, okay. I said, okay, I'll save a little face, I'll stay a business major, I'll go business, okay? So I'm still going to be a banker, but, I'm still, not as quite as high as everybody else is. So then, I go to state and enroll in all these business classes and core classes to begin with, and then I did this my personal discovery in my freshman year, and it's personal because I found the cure for insomnia, and it wasn't pharmaceuticals. It wasn't exercise, it wasn't yoga, it's economics. Put the economics book beside me and let me start reading it. I would fall asleep in 2 seconds. I'm like, this is guns and buttery guns, this is not for me. And so I was like, okay, well, I understand. So I'm like, all right, well, I don't want to be a banker anymore, this is definitely what we're going to do. So I'm like, what do I do now? Hey, don't want to be a lawyer, med school. Well, yeah, you can think about going to do med school. So I was like, all right, new path. All right, once again, I'm at state. Med school. Kiana does, my parents always told me. It's a new path. I want to start doing science and math classes. That's what interested me. And so I started taking engineering. I was like, all right, well now I can be an engineer, take engineering classes. After 2 years, I can transfer, be back with the family, go to UNC. Right? After second year, accepted to UNC. Guess what? Become a bigger black sheep. I like state. I like state a lot. It has all the good classes, up to science, engineering, and all that. So I was like, all right, I still like interested in med school and all that, but I want to stay an engineer, so I want to become a chemical engineer instead. So I went there, finished that, took all the different classes, took a little bit over 4 years, the alternate path of college, and graduated from chemical engineering from state. So then I was like, okay, med school. Apply to med school. All that, all the rigmarole. Next roadblock, boom. Take it in med school. Take it in med school. All right, career path change again. What do I want to do? And I wait this. I'm not going to wait this. That doesn't prove you're going to get in. What you're going to do. So I did what any dedicated, path-driven, most motivated college graduate would do after they graduate college. I took 6 months off. I decided to hike the Appalachian Trail. I was like, all right. That's my parents were going to love me for that. But it was, it is a very educational experience. It teaches you a lot about yourself, and I highly recommend it. We're talking about other things for STEM, like other different career skills to have. Something like this is great. The physical and mental challenges that you come across, the endurance your body can get through as well. it was a lot. But it's also a good time for reflection. I mean, back in the day when I did it, we didn't have cell phones or GPSs or anything like that. It's a topo map with a compass, and that's it. You had a little Walkman. That was your entertainment, but the batteries were run out. What are you gonna do there? So it was definitely a self-discovery time. But on that thought, I said, okay, I still want to be in the medical field. I'm an engineer. That's what I do. So I finally was accepted back in the family and went to grad school at UNC for biomedical engineering. There I studied cardiovascular, but we're interested in pediatric congenital heart defects when they're born without pretty much the right side of the heart. And this goes really for what Dan was talking about earlier. I mean, Ohm's law, V equals IR. It's a huge thing, just what I was doing. We do pressure and flow, same thing, current voltage. So we measured resistance in the different arteries. Then we measured impedance and calculate the energy required to push blood through different vessels. And so even your basic Ohm law, the basic equations in life, you just learn from, well, I don't know what grade you learn in law. But it still comes back to using, as far as math. You're going for your transforms and all that back in that day. Well, that's different. I mean, it's still the basics. But that, as I was in grad school, I was actually grad student poor. So I decided to get a job as well. And I got a job at a company called Oriel Therapeutics in the Research Triangle Park. And what they did is design dry powder inhalers. They went on to branch out to be Cirrus, it's a big company, they have a TEP as well. And all that. But the founder of that company was a pharmacy advisor at UNC. And so I started working for him and worked that. And so I use the same principle of fluid dynamics to model airflow through inhalers, and design inhalers, and to do powder to see particles to see where they go, and to be able to basically emit all the dust. And so I did a lot of design of that, a lot of stems from the CAD to the design to the fluid dynamics, to the math, to the equations. So that's where I basically started my interest in the pharmaceutical side of the medical field. Got my degree, and I got hired out of grad school to Dr. Dickinson. I don't know if y'all know Dr. Dickinson. They're in the park. People always say it's the largest company nobody's ever heard of. And they heard it. If you've ever had a shot, you use BD. And every needle, every syringe, they bought everything. I mean, you look, everything they open in a hospital, it basically says BD on it. It's always a BD product. They're huge worldwide company. They didn't hire me for different reasons. They hired me for my chemical and biomedical engineering. After 9/11, they got a joint partnership with USAMRIID, which is United States Army Medical Research Institute for Infectious Diseases. They love their acronyms. But they got there they had a need for dry powder pharmaceutical countermeasures to bioterrorist threats. So if somebody came and did a smart bomb for anthrax, or a smart bomb for anthrax, or botulism or plague, they needed somehow to get pharmaceuticals to their quickly. It could be in the jungles, tropical forests, or it could be in the deserts of Iraq. You never know. So it needs to be able to survive humid conditions as well as hot, sandy conditions. So they hired me and a couple other team to work on a drying method for pharmaceuticals called atmospheric space freeze drying. I'll get to that later on. But what it is a dry powder pharmaceutical, and that stems into what this will be in a second. But so we designed that and designed shelf-stable, 2-year shelf life vaccines for 5 different, terrorist measures. But then we got that project ended, and it was a success. And BD's like, okay, that's great, but we don't make drugs. We are a device company. We make needles and syringes. So this is not part of our platform. And so me and part of 2 of my bosses, which were part of the team, engineered biopharmaceuticals. And so then I came here, and we got a National Institute for Standards and Technology grant, which is a technology innovation program that's now been done away with. Last couple of years, it was manufacturing excellence program or something before that. But we have a joint commission with them and the Tobacco Commission to bring biomanufacturing and technology jobs back to Southside Virginia. And so that's what we did. We started, it was a 3-year grant, and the goal was to bring manufacturing, high-tech jobs back to the U.S., as well as bring tech jobs back to Virginia, because Virginia had just lost the Dan River, and lost the tobacco. they want to bring high-tech jobs in the next wave of the future. So our goal here was to, by the end of that grant, to build a pilot-scale manufacturing line. So what do we do at Engineer Bio? We consider ourselves dry powder experts. So we take a client, company, world, country's problem, issue with pharmaceuticals, and we don't just say, let's make a drug. We make an engineered solution for it. Because usually it's just, nobody communicates. It's like the drug people make this, the device people make this, the other people do it, and nothing ever comes together, and it comes together and it doesn't work. And so what we want to do is tie all those different areas together, from the formulation to the finance, to the manufacturing, to the chemistry, all of that, to make a dry powder pharmaceutical to satisfy the need and to deliver it to where it needs to go. I guess that's the more important thing. But most people just say, okay, give them a shot. But that's not the answer anymore. People want personalized medicine. People want target-specific medicine. People want it at their door. If a nuclear reaction was, I'd actually order it to your door, right? If you only be able to administer it yourself. You don't want to go wait in line at the doctor's office and go for a shot. You want it instant. You want it to be mass stockpile, storage, to be stable, for the national stockpile for different types of plagues or flus or whatever. So that's what we do. We match the person's formulation, we make a dry powder solution, and we formulate it to that specific drug, that active. And then from there, we say, okay, how do we want to administer it? Is it better to administer it this way, or this way, or this way, or this way? And then we design the device, or the route, in parallel with the formulation. So everything by the time it ends is optimized for a total solution at the end. People say, you're an engineer BioPharmaceuticals. Where do you work? Danville. Why are you in Danville? What is in Danville? That's a good question. I get that all the time. There's an answer. Number one, location, location, location. We are right between RTP, which has big pharma all over the place, and DC, which has government all over the place. So that's the huge thing. We're sitting here around, how many major universities from, Duke, State, Wake, Clemson, not Clemson, but Virginia Tech, Virginia, all the different community colleges, all that are right here. As you say, AutoCAD's another good example of DCC. Jerry Franklin used to, I don't know if y'all know him or not, he just retired recently over at AutoCAD. He was a huge integral player, finding me all about additional employees for the manufacturing, production tax, and all that. And it's a great symbolism, symbiotic relationship. The Institute as well. We have a lab over at the Institute. We have a lot of different equipment that we use, a lot of new equipment we share, a lot of resources we use. It's a lot of knowledge. We've gone out to governors, to BARDA, DARPA, all the big players on how to help. What do they need? World Health Organization. What do they need? How can we help them? With partnerships with different labs, different diseases. The reason we came here, we do the economic development. We do down in North Carolina, Jeremy used to be economic development, who's now gone, but he went from Rocky Mountain up to here, and we followed him. And we loved Gable's aggressive tech-oriented vision. Get rid of, tobacco's gone, get rid of it's gone. Let's bring in high tech. We go about different kinds of fuel, biomass. In our building, there's a biomass, Titan Biosciences. They're right there in our building, Broughton Danville. Ireflex, high iron glass. They're bringing a whole bunch of different new high-tech jobs to Danville. We're excited to be part of that mission. Support systems, City of Danville, Community College, where we are right now, the Dan River Business Development Center, which is an incubator. It's great. It's a great city for that to happen. Just as what they were saying, the motivated workforce, but they don't have the STEM technology. They were in the cotton mill. They were doing that. They do not have, he said, basics to be able to read a ruler. That's the goal. We've been working with Jerry, with DCC, and AutoCAD and all that, to help train people to come in with the basic fundamentals. Without the basic fundamentals, we had somebody really getting, real paper and doing plots on graph paper. Well, yes, we can do graphs on computers. It's just little things like that. It's kind of hard to do. It's just that's the things that need to change, but that's the way they've done it. And so it's hard, but I think that Danville's definitely making a transition over. and it's doing a really good job. And I've seen it in the 4 years, 5 years I've been here easily. And just to help with, and they'll come to our company and say, what do you want? How can we train employees to come work for you? And that's great. I mean, so you can work in a relationship. As I said, we're at Day River. The goal is to build a large-scale manufacturing facility in Cyber Park. We're working on concurrently with different client products, but we're also producing our own products. And so we're working parallel, different like a suite type building where different suites have different types of drugs. Some drugs can't be manufactured at the same sites as others, and stuff like that, all the details. But the goal is to have a footprint in Cyber Park, India. That's who we are. What do we deliver? We, as I said, small molecules, that was the wave of the past. That's everything you go to Walgreens or CVS and buy over the counter. It's your aspirins, your leaves, your all that. But that's a systemic drug. It's no longer target specific. So as I said, medicine is changing. It's more going towards peptides, large proteins, monoclonal antibodies, stem cells, DNA, RNA, a whole bunch of different high-tech, high-precision drugs that are target-specific to a certain cell, to a certain protein on a cell, to a certain membrane, to everything. And so what we do is we are able to take our technology allows us to take all of these and make dry powder dough. It will take formulation. It will take the target. We've got to take all that into consideration. But all the, the STEM systems behind all this. The chemistry, the basic formulations, the conversions. Being able to convert, metric to, it's just anything. So they're doing, inches. We don't do inches. We do centigrade. We do meters. We're in a whole different world. We don't do Fahrenheit. They need to be able to do that. They need to be basic stuff and understand the difference and be able to convert them. And as you said, measure twice. We have to keep measure. Same thing. We've also, one good thing about our technology is nutraceuticals. Certain things in chemistry are isomeric. And so what they do is like vitamin E, for example. And one isomer, it's active, but if you put it in the sun and all that, it'll change isomer, it won't be active, it doesn't do its purpose anymore. So you take all your vitamins and put them on the hill, you're basically taking quite a waste, especially if it's in a clear bottle. Stuff like that. Omega-3 is the same thing, how much is in there? But we focus on different things. SAMe is a big one for different types of diseases. We also, so I'll get to later on, doing different consumer products. A lot of people look at our powders are different reconstitution, fast reconstitution. People take Metamucil. How many times you put a little thing stirred around, it sits at the top. It sits there. All your energy drinks, all that. So we can formulate our particles to dissolve really quick and to go into solution really homogeneous. All right, so here's how do we deliver it? We make small spherical particles that we can control the morphology. All these those are three. These are all images of our particles, except this one, obviously. That is pictures of colored beads. But so these show a blend. A good way to show a blend, for dengue virus, is like different four strains, or the flu has 4 or 5 or multivalent. And so what you want to do is you could draw those powders separately and blend them together according to say, okay, this year this strain is bigger on the flu than last year, so let's blend it for this. And I already saw a thing on the news today, the flu is going to be really bad this year. So go ahead and get your shots early now, because it takes time for the immune system to respond. Don't wait till flu season. So these are the advantages of how we make our spherical particles. This is the novel atmospheric space freeze drying. What we do is we atomize, I'll show you a little later on up here, the formulation, liquid formulation, we spray it with different types of nozzles or different kind of atomizing devices. And then we freeze it, and when we collect it down here and we dry it through more of a convective drying, but it's also a partial pressure issue between the moisture, because we use a really dry gas as well, so there's a stem there, so it's a humidity. So it removes the moisture from the frozen particles through convection. So for a difference in moisture. And then from there, so it's inert. We have to use nitrogen because a lot of pharmaceuticals are very sensitive to oxidative reactions and stuff like that. So temperature, oxygen, water, all those things are bad for it, for the new wave of pharmaceuticals. But the being we try on spherical for different reasons. Consistency. We could control, especially for I throw a wiffle ball, I know where it's going to go. I throw a piece of paper, where's it going to go? I have no idea. You know, I can shoot. I know physics behind it. As he said, shooting that ball across the thing. I can predict it. I can predict it. So it's definitely well. As well as the parts same size. I don't want particles of different sizes, different shapes, because their response, more might agglomerate here, more might agglomerate here, so different reactions happen. We could do the Trojan horse. We can embed to full cells. We can embed the antigen inside of another cell. So the cell sees it and says, okay, I like you. And the next thing you know, it releases the antigen, and so it provides a new response there. Particle payload layering, kind of like the everlasting gobstopper. The way we want to go. Yeah, as you go down different things, make different pharmaceuticals release. And so we can say, okay, for initial reaction, you want this response. Okay, once that responds and this starts happening, so things still proliferating, we want this drug to release. And it actually goes on as well. Particle coding, that's more, we use more for surviving harsh environments to get through different systems until it gets to a location. And then it will release the drug there. So we can coat, we can make multi-layers like a core, like a golf ball. You know, core and rubber bands, and then only the rubber bands we're not, and then the shell. So that's how we drive. That's one way we drive. That's our novel process that we license the technology from BD and started with. And then I will pass around. Always love show and tell. So I have this. Our powders are very small and very low density. So they move like a fluid. So we can. Do not open, red label, do not open, there's actually a drug in it. Just the way folks that liability, no, do not open, do not open. But you can definitely see how it flows like a liquid. And so we can use a lot of the fluid dynamic properties to predict flow of our powders. I'll just pass that around, you can shake it to you. These are around 20 micron size, Excipient, a B diameter size. That is geometric diameter. We make, as you saw before in the previous slide, difference of a math, we make porous particles, right? So we make wiffle balls. We make different types of wiffle balls. So it has a geometric diameter of 20 microns, but has an aerodynamic diameter of something different because it's due to the density. So it's more, it would act like a 5 micron particle, but it's really a 20 micron physical size due to the density. One way, those kind of way people, we make powders for it, oral delivery. Why? We mainly deal with class 2 and class 4. For oral, a lot of oral drugs today, they give you 500 milligrams when all they need is 5 to get to a reaction because it all gets, the bioavailability is so low, or it's not soluble. So what we do is we add excipients, which is different ingredients to the recipe to increase the solubility of the drugs. All the chemistry and all that comes into play, all the polar, hydrophilic, hydrophobic, all those, you can put interactions between them, all that is really key for this. So what that does is allow, when we increase the solubility, we therefore increase the bioavailability, which in turn lowers our dose size. Okay, so now I don't need 500 milligrams, I only need 5. So now I don't have 500 milligrams going out throughout my whole body, which reduces the side effects. I mean, people take a big one, like people take albuterol, they get headaches, they get tremors, they get shakes. I mean, caffeine, the same thing, it happens, especially, so it's a systemic relaxant when all you want is a focused target reaction. And so that's what we do. Talk about the coatings, target-specific example. There's a bunch of biodegradable polymers and that we can use to dissolve at certain pHs. And so it'll survive the stomach, the harsh environment of the stomach at the low pH, and then once it gets into the intestine, it'll release there where all your immune system is, all your Peyer's patches and all that for the intestine, so you can actually get the immune response there. Or you can have it survive and go all the way to the colon for something like Crohn's disease, colonitis, anything like that. So it's a different form of doing a suppository. You could be doing an oral drug. Great part about our thing, it's very flexible. I mean, we can manufacture our dry powder in so many different forms. We can make a powder, we can compress it into a tablet, we can load it and put it into capsules. We put the powders into soft gels that are different coatings. We can put them in liquid suspensions, emulsions, nano suspensions as well. So how do we test the efficacy of this? We put them in animal models. So that's how we do the toxicology. Is it harmful to humans, harmful for rats, is we could have, what dose do we need? What dose is required to get the response? And we can also formalize our formulations for it. A great job for anybody who wants it is filling these capsules. We have to do these for animal studies. I'll pass these around as well. They are very small and very tedious. They make those enteric coated as well, so it can survive, the capsule material can survive the stomach. So it's a lot of chemistry and science behind that as well. Yeah, they take a pill gun and put it down the rat and administer it that way. Or you can do a gavage as well. So that's one way we make drug powders to oral delivery. Another one, nasal. I'm going to stay here biology, the technology here. The problem here is we don't need those really small micron sizes because it can cross over the blood-brain barrier. We do not want that. There's a lot of complications, FDA nightmare, right? And so what we want to get to do a larger particle size, more between 10 and 100 micron, that will deposit in the NALT space, which is the nasal associated lymphoid tissue. And y'all know the lymphoid tissue is where the immune response gets. And so there's a really big area, especially in kids, especially for us, in the nasal region for the immune response. And we have a lot of drugs are trying that out to get to that, are being developed to see if they can be delivered through the nasal vein. It's attractive, one big reason right there. Kids, no needle, right? So what we did is BD helped develop the end to the flu mist along with metamine. And so the tip on here, the tip on here is actually an atomizer, an aerosolizer. It makes a fine mist spray, then when they put it in the nasal passage and spray it, it basically coats the knob there, right there. And we add excipients to it to let it stick and let it stay longer, so the response is greater, the time there is greater. So it's another chemistry, which is mucoadhesive effects and break down the cell membranes to be able to get to the receptors, be able to get to the B and T cells. So we'll pass these around. These are the fluid mist containers we designed. It's just a really small atomizer there. Fluid dynamics, it's not dynamic, they're atomizer. Like the spiral, it's kind of how it goes, how the mist comes out. Another prototype for nasal is take a capsule like this, small capsule, fill it with powder that you would want to, put a thin film of plastic on it, be able to attach it to a syringe, right? Or you can fill it with a liquid. And then you add a tip onto it that locks in place, and then just force it. The air pressure will shear and break the plastic, and the powder will come out in the flume. And you can change the geometry of the plume by the nozzle tip. These are all prototype parts. But it's just different ideas that we do. It's just to show that we got the ability to do the drug. We designed a device to go with the drug. These are as well. What we've concentrated more than anything, I guess, in our company is pulmonary route of administration. Because we have such controllable morphology and the science behind it. I mean, all the different process parameters, the freezing rate, the nucleation rate, the annealing to be able to crystallize the structure, the amorphous versus crystalline. The science behind it is I mean, it goes so many different levels. As you said, it's multidisciplinary. So with the main advantage, we avoid first pass metabolism. We don't go to the liver when we go to pulmonary. Because you go intestine, it goes to the portal system, hepatic system, then it goes to the liver, and most of it gets destroyed. Right? If you go down the lungs, you're basically on a cell-to-cell basis with blood. Right? You go straight to the heart, and it gets pumped out. Right? So the transfer is very efficient. Target specific. This is a good thing to show. Different size particles, aerodynamic size, can go to different locations in the lung. If I want to treat, asthma or TB, I want to be in the middle section, right? I don't want to go deep lung. I want to go where the asthma is. I want to go to the bronchioles. I don't want to go. That's why you get your jitters and your headaches, because it goes everywhere and it goes systemic instantly. If I can make it targeted just right there, it will just have no side effects. Same with IPF, idiopathic pulmonary fibrosis, same thing. Now we want to go deep lung, because that's where the scapula is, the alveoli region. Lung cancer is different areas, different tumors. You can tailor it toward it. as I said, we reduce the side effects. There's some vaccines in development. There is an anthrax vaccine out for pulmonary. It has not been approved by the FDA. But there is a lot of people who are looking into and developing different types of pulmonary drugs. Big one out now, inhaled insulin, a freezer. That was just FDA approved a couple of years ago. My bosses that were on the team that helped develop these, that's why I'm showing these. They developed these devices for inhaled insulin. And these are the little cartridges that they load up the insulin in. These are empty, there's no drug in there, prototypes. But they also do the cricket. This is for a multi-dose. What you do is take one of those capsules that are loaded with the insulin. This has all been designed by the CAD, by the SolidWorks, by all the things that Kevin was talking about. All designed in-house, and the skills are so critical. Different prototypes. Now you can see they're made out of different materials, different stages of a prototype. But put the cartridge in, close it. It opens up the cartridge, inhale it, done. You can take that out, put it away. It's a lot smaller than your inhaler, right? It's not a shot. You don't have to do that. So you can just carry it in your pocket. You can carry 12 doses at a time. Or, I was going out for the evening, right? This is the single dose throw away. Look how small that is. You can put that anywhere. I know whatever in there. So the capsule's already in there. All you do is push it forward, breathe, you're done. Throw it away. Single use. So I'll pass these around for people to look at too as well. But then this is a prototype. You'll see our engineering workings and stuff where we're studying different things.
Is the plastic that you make for that recyclable plastic? Because I'm thinking of throwaway stuff in terms of, now you're collecting that if there's a way.
Good question. I know it is coated for static issues as well. So that's a big issue with low density dry powders. It has a coating to reduce the static as well as when you breathe. So I don't know if that will change the properties or not. So that's a good question. Last but not least, what we focus on for powders, injection. People hate a shot, it's still the industry standard, right? So we make, these are our particles right there, we make dry powders to both in a powder form and in a lyophilized cake form. We make those small particles or we dry them as a whole, is what you see it usually in the doctor's offices, where they put water for injection, shake it, wait till it turns a certain thing, and draw it back and do that. So these are actually from a different vaccine. These are test formulations for a rabies vaccine we're working on with the World Health Organization. So there's no drug in there, but these are just plus it's caps. So we have a line that we make these. So different. See the difference between the cake and the powder. But this is a lot of science to it as well. All the different glass transition temperatures between the sugars and all the different stabilizers that are in there. The melting point, the freezing point, the enthalpy, the amount of crystallization upon storage. All these things have to be determined and are factored in, both from the front end and through experimental design for each of these formulations. Okay, so what's the example? This is a good thing to show you. We'll show you, we built a manufacturing line, a pilot scale manufacturing line. Talk about all the different STEM. We designed and built that ourselves. Multidisciplinary, there was 6 pharmaceutical, highly mechanical, electrical, programming, all that disciplines are needed for that. I mean, we did a lot of stuff, what we could get done locally, we did done, like a Piedmont made their table, we got a lot of stuff done, but the pharmaceuticals, the vendors are very select, so you have to go outside of them. But we we do this aseptically, so we put these in isolators. So we built a clean room in our bay, and then within the clean room we built isolators. So there's no human contact. There's ISO 5 inside, ISO 7 in the clean room. I don't know, they changed the numbers just around. That's our particle characterization lab, our formulation lab. I'll show you that. You've seen the ASFD, atmospheric spray freeze drying. These are the other capabilities. Industry standard I said was lyophilization, the cakes. That is this. How they make drugs is a different. We use convection and driving force as a big other driving force and humidity. This uses sublimation, the vacuum, the pressure is the driving force. So what it does is it freezes it, it draws a vacuum, and sublimation. It's kind of like Everest. You look at the top of Everest, you see the cloud of mist over there because there's some swabbing off with the blood pressures up there. That's still industry standard, trying to show the game. This is spray drying. This is a different technology. It uses heat, evaporation. to remove the moisture. This was great for all the over-counter particles. Proteins don't like heat. Don't like heat at all. They denature. They're irrelevant. Once the conformation changes, they're worthless. So what we do is we lock those proteins in the conformation they are, and then we remove the moisture, keeping the proteins in the same shape. So we have something called an FTIR instrument for transfer infrared, and that can tell us the three-dimensional shape, the alpha, the beta sheets, all that, alpha helix is the beta sheets of your proteins. So you can see, and we also can test the HPLC if the protein is still active, if it's a monomer or a dimer or whatever it is. So, and this is a DSC, differential scanning, that does all our thermal events. To your melting point, heating point, glass transition as well. So that's what we have here in Danville. Talk about schematics, be able to do engineering drawings. We do them all day long. You got to be able to read them. You got to be able to know the symbols. You got to be able to measure and to do it. I mean, if it's basic, we start out with basic. You know, what 2D we go through. You got to be able to do it. You got to be able to understand and read them. Critical for us.
What CAD system are you using?
We use SolidWorks.
SolidWorks?
Yeah, I don't know. There's too many Rhino. I don't know what y'all use.
Primarily in this.
Yeah. There's tons of them out there. Whatever people started with and got familiar with, that's basically what people use. I mean, some engineers use AutoCAD. Some people use SolidWorks. It's just
Yeah,
what
I
they're,
did a number of years on AutoCAD.
right. It's just what they're familiar. What we decided, what we discovered in this, as we got 2 minutes. All right. Okay. Well, we also said we retain a lot of properties, which is we've also got to the food and beverage market. If y'all want to afterwards, you can come taste. I've got orange drink, a coffee, and a lemon lime drink here as well. So if you want to taste those, because what we do is we contain the volatiles really well. So you don't only get the taste, but you get the smells and the aromas as well. Like coffee, it's the coffee. Everybody hates it. But we can do coffee really good. But it's really strong coffee, just so beware. We're talking about STEM. The 2 minutes ago were these 2 things. A lot of things were covered by them. Through negative fundamentals, everybody knows, basically everywhere. Basic computer skills. And that's more for the older generation trying to get into the workforce. But it's still basic. You have to be able to do it. You have to be able to write Word. You do Excel. You need to know it. Then the younger generation, basic finance. They don't know how to do a budget. They don't know how to estimate materials, the cost. They need to learn how to do that. As he said, creativity is huge in our industry. Think outside the box. How many ways do you throw a frisbee across the river? Ask my kid that yesterday. Travel around the world. That was his answer. That's thinking outside the box. To the other side. You know, it's not throw it across, float it across. Scientific method. They need to learn how to follow it. You learn how to do it. Not to be to the ladder. They need to learn how to do it and get up a rational design of experiments in order to solve the problem. They've been talking about this all day. Theoretical versus practical. I can sit in the office all day and do quadratics and all that and differential equations. Go out there and try it. See what happens. You know, put your hands on it. See what it does. That's so much more valuable. To a quicker solution. Hands-on experience. Come to these workshops. Go do their internships. Go classes. Lifelong learning. Writing skills. People come out with these science degrees on that. They can't write. It's terrible. I'm like, how do you convey results? Writing. Organization skills. We've got multiple projects going on. The ability to handle it. This is the big one I have to teach my other employees. It's okay to fail.
Yeah.
You know, it's okay to fail, but fail fast. Fail fast and learn from it. And use those applications. Why did it fail? Don't make that mistake again. But it's okay. Last, just other soft skills. Everybody knows the basics: communication, leadership. I like flexibility. I'm a startup company. You know, I'm a janitor one day, I'm a formulation chemist the next day, the machinist the next day. I don't know what's going to be. It's going on what project, what we're doing, who's short, who's doing not. So learn jack of all trades. Don't just focus on one field. That's huge. And things change. The company's vision changes. The company's scope changes. The project changes. I'm with one team that I've been with for 10 years, and then my boss says, okay, go work with them. I got to be flexible and say, okay. You know, that's their personal skills. You got to be able to work well with people. Yeah, not necessarily a mentor and boss, yes, team will work critical. You know, but you don't use the communication skills for your boss. Time management. A lot of new employees don't know how to meet a deadline. They don't understand that we have clients and people are waiting on this. Things have to happen. You know, it's really critical. And last but not least, it's not your life. Work on it. It's a passion, that's fine, but also have a good balance between it. I think that's That's the way we are. That's, you know, I have a family, go home too. So. Jobs for y'all, internships, employment, send them our way. I'm open for tours. I'm open for come talk to y'all. Huh? There's so many different areas. When you look at other different areas, I mean, even the basic, like middle school and high school, I mean, we can start slow. We can start with a program in Arduino or Raspberry Pi. They don't have to be able to do complex. You know, they don't have to be able to do SolidWorks and all that. But they can just start the basic skills of it. But, I mean, we can do, I mean, little calibration curves, do little, you know, titrations, things in the lab. We can give them that. I mean, we're open all the time. We do, I've done internships at the governor's school here, the AET program. I've given tours for the different camps that come in the summer. They come over for tours. It's the third graders to fifth graders that come in. That's more of a countywide, I think. So the door's always open. Come over to DRBDC, email me, say you want a tour, say you want to come in. It's great.
You did a thing for teaching.
I have done, I did a thing for teaching.
I went actually, we went in the clean room, we took up on a tour.
Yeah. Is that the beer and bioscience?
Yeah.
Yes, beer and biotech.
Yeah.
Yeah. We did that a couple of times. That's a really good way to show we're here, damn. You know, that we're available. That's it. I don't have a question mark. I always have an open door. So I just say come. Yeah. Don't. I have boys. You know, why did you tell me that? My door's always open. Come ask.